Okay, if you remember, the goal of this lab is to come up with a way of automating the display to where it looks like one continuous flow of digits instead of having to press the buttons on the display to get each digit to show one at a time. So we're going to do that with a couple of modules. We're going to use a counter to divide the clock frequency down to something reasonable. I showed you the video where we were looking at the refresh rates for displays. Well, these 7-segment displays are displays, and so rather than updating the display at a 100 megahertz rate, which is way too fast, we need to slow that down to something more like 60 hertz, so it's a significant slowdown. All right, we also need to turn on the anodes for each of the displays one at a time, so each digit updates, and you can see that on the display, and we rotate through that to get a continuous looking display. All right, so we're going to talk about those two modules. All right, but first of all, I wanted to talk about how you implement a state machine in Verilog. A counter is an example of a state machine. All right, so these comments apply in general, not to just this counter. All right, so there are 3 components that I've highlighted in different colors here. First of all, there's next state logic, which is combinational, okay, like we've done in the first part of the course. It doesn't use flip-flops, it's just, think of it as the AND gates, OR gates, that kind of thing. All right, very little delay time between input and output. It's just the transition switching times of the gates. Then you have the sequential part, that's the flip-flops. So remember in class we designed a little 2-bit counter, and we had these D flip-flops and they were clocked, and we came up with the input equations for the flip-flops to make it do the counting operation. All right, and just, let me put a timeout here. Remember what a counter does. If I had a 2-bit counter, it starts at 0, then it goes to 1, and then it goes to 2, and then it goes back to, then it goes to 2 1s, and then it goes back to the top. All right, so 0, 1, 2, 3, and it just rotates in that fashion. Okay, so that's what a counter circuit does. So let's move to the description of that. But before we move on, there's also a side note. This is a block diagram for something called a Moore machine, where the outputs are a function of only the inputs and states. There's another machine out there that's called a Mealy machine, where the outputs are a function of the states and the inputs. All right, so for now, let's talk about this Moore machine, because that's what we have. Okay, so here are the different components of the code that implements the counter. All right, so first of all, let me walk you through some interesting things about it. The first thing is, this is a parameterized model. So we're going to have n equal 4 as the default, is how this is written. And you can instantiate that with different levels of count. And so you see that showing up in the output list. So one of the things that comes out of the counter is the count. And so this is an n-bit counter. It goes from n-1 down to 0. And if you had n equal 4, it'd be a 4-bit counter. All right. And then in this particular case, we're going to have an output that divides the clock. So we're going to put a tick, an output that shows up every time the clock gets to the end. So if it was a 2-bit counter, remember, here's our sequence for a 2-bit counter. When you get both of the count values to be 1, the output would be tick equals 1 in that particular case. All right, so if you had, a 20-bit counter, it's going through and it's counting. It goes through all the way up to, 2 to the n minus 1, and then it gets to the end and it puts an output out. Okay, so you can see where you can slow down the clock by just having a bigger and bigger counter. All right, so next, what I want to talk about is the different sections of the Verilog code that implements this state machine. I talked about the red part being the state memory. The blue part is the next state logic. You can see that here. And then the gold part is output logic. All right, so some interesting features on the state memory. First of all, it has two things in the sensitivity list. It's got the positive edge of the clock. We expect to see this. This is the synchronous part of the system. But in this particular case, we're also sensitive to the reset. So this makes this an asynchronous reset because it's not synchronized with the clock. All right, so anything that shows up in the sensitivity list that doesn't involve the clock, that forces that part of it to be asynchronous. Okay, so here's the logic on this. If reset is equal to 1 on the positive edge, we run the sensitivity list. If reset is equal to 1, the counter value goes back to 0. Otherwise, the updated memory is coming from the next state logic, Q next. All right, so that's the role of the next state logic, is to implement the value of Q next. So you see Q next here, it comes from this block. Q next is updated in this block. All right, so when we look at our next state logic, the sensitivity list includes everything. That's what the wildcard asterisk means. Okay, and in this particular case, if enable is equal to 1, then we are just going to count. So the next state of the count is the old state plus 1. All right, however, else, if enable is equal to 0, we don't count. We just hold on to where we are. We don't make any change. All right, so that's a counter with an enable. All right. And then finally, we get to our output logic, which is also combinational. Notice the equal signs are regular equal signs within the next state logic. The equal signs are the non-blocking statements here. These are blocking, these are non-blocking. Okay, so again, blocking statements on the output logic. In this case, it was such simple logic, we didn't even use an always block. We just assigned it. We assign the count to the Q register, and then here's an interesting notation. This N here repeats this binary pattern. All right, so N extends the 1 to N different bits. All right, so basically, if N is equal to 2, this would be 1, 1. If N was equal to 3, it'd be 1, 1, 1. Okay, so it's testing here. It's a conditional assignment. It's testing if I get to the end of the count, I set the tick equal to 1, otherwise this tick is equal to 0. All right, so that's generating the tick that we're using to slow down the clock. Okay, so that leads us to the circuit setup that I want to have. I want a counter that's dividing the clock and gets the tick down to a certain rate. Okay, and then what that will do is go into this anode encoder that I want you to write yourself. All right, so for this anode encoder, I want you to take the counter and modify the output. Okay, use a 2-bit counter because we have 4 anodes. 2 bits gives you 4 combinations. Modify the output assignment. All right, so at this point, let me go through the logic on what you would need to do in order to modify the output. Okay, let's go through the timing diagram so you see how this should operate and you can come up with the code to implement the anode encoder. All right, so Q0 is the least significant bit, and so this is a counter. The least significant bit is going to change with every clock edge. All right, so let's say we started with Q0 being a 0. On the first clock edge, it's going to go to a 1, and it's going to alternate. Every clock edge, the least significant bit changes. So that's straightforward. Okay, and then Q1 is the most significant bit, so it's going to change on every other clock edge. Okay, so not the first one, if we start at 0, not the first one. All right, it's going to stay at 0, and then it's going to go to a 1. Whoops. going to stay a 1. Every other clock edge is where it changes. Okay, and so we could put the values in here. This would be 0, 0, 0, 1, 1, 0, 1, 1, and then we start over. That's a counter. All right, now let's look what happens to the tick signal. All right, let's put that in red. Now let's make it purple. Okay, the tick signal is going to be 1 when both Q1 and Q0 are 1. Otherwise, it's a 0. So I'm going through here. I want it in purple. Tick is a 1. Tick is a 1. Okay, so I generate the tick signal. All right, next, let's assume that we started with, let me move these signals over a little bit. These are the decoded anode signals. So let's assume we start with the 0 position on, and so all the others would be off. Okay, so off, off, off. Okay, so ANP0 is going to stay a 0 till I get the next value of the count for the anode encoder. All right, on the next value of the count, this should go to a 0 and stay down at a 0. Because I incremented the counter, after I have a tick, ANP1 should go high. And it should stay high till I get another tick. It stays high all the way to the end of the tick because the tick is what enables the counter. So at the next edge of the clock, the count from the anode encoder is going to increment and takes this stack back down low. All right, so that's what we have here and here. And then finally, let me move this signal up a little bit. This is going to stay a 0. And when I get to the input condition 1, 0, at the edge of this tick signal, the 2-bit counter inside the anode encoder is going to increment to a 2, and it's going to stay high until the next edge of the tick signal. And then finally, 3, I need to move these up to get the 0s away from the 1s. Okay, and finally this is going to stay low until the edge of this tick signal, when it will go high. All right, so what we're seeing here is the anode signal gets turned on one at a time. These are like the button presses, you know, on, 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 and then it circles back around. So it turns each of these digits on one at a time. All right, so you need to modify the counter circuit, make it a 2-bit counter because we have 4 anodes. All right, and then for each output state, do the logic that gives you this correct signal. All right, so that should get you going, and I'm going to have you do a test bench for that. All you need to do is instantiate this model for the test bench. All right, so I'm giving you the model. I'll give you the code for this, but you have to tell what all the input connections are to instantiate the code. All right, so hopefully this helps you come up with the timing circuitry for our display.